Hey guys, welcome to Lesson 9-2, Multiplying and Dividing Rational Expressions. This is Mrs. Brunk. So we spent some time looking at graphs of rational functions and applying some rational functions to some real life situations. And then most recently we've added and subtracted rational expressions. Today we're going to continue working with rational expressions and exploring the operations of multiplying and dividing. And much like when we looked at adding and subtracting the rational expressions, we're going to look at a numeric example before we get into ones with algebraic expressions in the numerator and denominator. And so kind of think back when we did multiplying and dividing with fractions. It seems funny that back when we learned that, probably in elementary school at some point, that we didn't start with multiplying and dividing. Because if you remember, it really is much easier to multiply and divide fractions than it is to add and subtract, because the one thing that you do not need when you multiply and divide is a common denominator. And that was really the challenge in this past lesson was, how do we get a common denominator when we have polynomials in our denominator? So this promises to be a much easier lesson. So how do we multiply something like 4/5 times 5/6? Well, we simply just multiply straight across. And then again, that's the beauty of multiplying is you multiply the numerators, you multiply the denominators, and we would get 20/30, which could then be reduced to 2/3. Now what we could also have done instead is to reduce these fractions first by doing cross-canceling, reducing, prior to doing the multiplying. So what we could have done is see how there's a 5 in the numerator here, and there's a 5 in the denominator on the other side. So I could have just canceled those out. I could also reduce the 4 and the 6 in the other positions in the other numerator and denominator by a factor of 2. So I could divide out a 2 out of the numerator, leaving me with a 2, and out of the bottom, leaving me with a 3, and there I end up with the exact same answer of 2/3. Now, in the case of multiplying rational expressions that involve variables, like the ones we're going to be doing, it's always better to reduce first, much like we did the second way, because sometimes these multiplications can get very cumbersome, so if there's anything we can do to reduce it prior to doing the multiplying, it's going to make our job much easier. So based on the steps used for multiplying rational numbers, how can you multiply the rational expression x plus 1 over x minus 1 times 3 over 2 times x plus 1? Well, first thing that you need to know is when you have a rational expression that has a sum or a difference in it, that entire term is like it's a whole piece. Like this x plus 1, it's not an x and a plus 1, it's an x plus 1. And so anything that could cancel out with that x plus 1 would have to be the exact same x plus 1. And so looking at these, you can clearly see there's a x plus 1 in the numerator and x plus 1 in the denominator on the other side. So you can reduce, as long as they're in opposite positions, whether they're in the same fraction or whether they're in separate fractions but in opposite positions. So one in numerator, one in denominator. And that appears to be the only thing that can reduce, and so when I go ahead and multiply the numerators, all that's left is a 1 here. And let's just remember that when you do divide something by itself, which is what we're doing when we cancel, really there's 1 left. So this is really 1 times 3, or 3. And on the bottom we have a 2 times x minus 1, which we could write as either 2 times x minus 1, or we could go ahead and distribute that 2 through to simplify the denominator. Now, as we kind of look further at more complicated versions of these problems, it's probably not going to be a good idea to go ahead and multiply that denominator actually out. So rather than distributing that 2 through, we would just leave it the way it is. And the reason why is then it's easier to look at and tell what values would make the expression undefined. And we'll be asked to state those things. So leaving it just like this is perfectly fine. So multiplying rational expressions is similar to multiplying rational numbers. Likewise, dividing rational expressions is similar to dividing rational numbers. How can you use the steps for dividing rational numbers to divide rational expressions? Well, similarly to with multiplying with rational numbers, we just would simply multiply the numerators and multiply the denominators. But when we do work with dividing fractions, remember we would just simply change it to multiplication by changing it to multiplying and then the reciprocal. So for instance, if we had something like this, 4/5 divided by 8/5, I could just simply change that to 4/5 and then change the division to multiplication and flip this divisor now and rewrite it as 8/5. I'm sorry, 5/8. And then I could see if there's anything I could do to reduce and then simply multiply the numerators and multiply the denominators. So clearly here I can reduce the 5s. I could also take a 4 out of 4 one time and out of 8 two times. And this would simplify down all the way down to just 1/2. So again, just really one step beyond just multiplying. So kind of the prospects of these problems seem much easier than the ones with adding and subtracting because you can just kind of take them the way they are. You can accept them right the way they are. You don't have to change denominators or anything, and we can just start right away with the operation. So we're going to go ahead and look at our first full example. So example 1 asks us to find the product and any excluded values. So let's read this kind of setup here for the explain. To multiply rational expressions, multiply the numerators to find the numerator of the product, and multiply the denominator to find the denominator. Then simplify the product by canceling common factors. And I'm just going to say, I kind of reverse that. I want to do any canceling, reducing first. I think you'll see why. And so I'm going to do that first and then multiply. So note that the excluded values of the product, so again this is kind of what we're going to look at to see what would make it undefined. So the excluded values of the product, which are any values of the variable for which the expression is undefined. So we're going to be targeting those denominators, seeing what makes them equal to 0 because those are the things that make it undefined. So really step 1 in my mind is to just do any factoring that you can do so you can see if you can reduce. So we did that with adding and subtracting on the denominator. We would factor the denominator just so we kind of see what we had to work with in terms of getting a denominator. But in the case of multiplying and dividing, we want to factor everything. See if we can cancel anything out to start. So let's see what I have to work with. So let's see this first denominator. I'm going to go ahead and factor that, and I can see that's an easy factor one. And that's going to be an x, let's see, minus 4 and an x plus 2. I see that on the numerator here of the second fraction I can take out a 2 out of each one of those things. So I'm going to take the 2 out, and that's going to leave me with, let's see, x squared minus 3x minus 10. And then normally I would go ahead and factor that further, that x squared minus 3x minus 10. But then I notice right away that that entire denominator is x squared minus 3x minus 10. So instead of bothering with factoring those, because of course they'll factor the same, I'm just going to go ahead and cancel the entire thing out. That just saves the step. And then just see if there's anything else I can work with. So otherwise on the top, what's left is a 2 and a 3x squared. And so going ahead and multiplying straight across, that's going to give me that 6x squared. What's left on the bottom is x minus 4 and x plus 2. And so looking at what would make the denominator equal to 0, I might mistakenly only identify the two numbers that make the final quotient denominator equal to 0. And so I might say x cannot equal 4 and x cannot equal negative 2. But I also need to make sure I look back at the original problem and see how this denominator here, and again this is where I probably should have just factored anyway. If I were to factor the x squared minus 3x minus 10, I could factor that, let's see, x plus 2, x minus 5. So I see another x plus 2, but I see an x minus 5, which means that 5 would also make one of the original problem's denominators equal to 0. So I also have to exclude that. So really it's probably a good idea before you start doing any canceling to identify all the things that would make the denominator equal to 0. Because in the end they would really make the entire problem undefined. And again, as far as I'm concerned, I think it's smart to just leave your denominator undistributed out, because remember from the prior module, that what those things do tell us are things like whether there's asymptotes there, and really any of these undefined numbers, 4, -2, and 5, will tell us there might be a hole in the graph there might be asymptotes, vertical asymptotes, things like that. Let's go ahead and turn the page. Now these next two were designed to be you-try questions, but actually I think I'm going to make just the second one a you-try. We'll do one more example together. I feel like more comfortable if we've done a couple. And so I'm going to leave this one as a you-try question. So looking at question number 2, find the products in any excluded values. So again, step 1 is let's just go ahead and do any factoring that we can do. And so I see that x squared minus 9 on the top. That's a difference of squares. I'm going to go ahead and break that down. That's going to factor into an x minus 3 and an x plus 3. I think a really good strategy is as you factor something, you should cross out the original because these can get kind of a little bit messy. The denominator here, that's going to factor into, let's see, I have to multiply to -24, add to -5, so that would be like x minus 8 and x plus 3. And again, these we can use the easy factor method on because they start with just x squared. The x minus 8 cannot be factored. Out of the second denominator, I see that I could take out a GCF, so I'm going to pull out that 2x out of both, leaving me with x minus 9. And then now I'm going to go back and take a look and see if I have anything that can be canceled. So I see there's an x plus 3 in the numerator here and an x plus 3 in the denominator here. I see that there is an x minus 8 in the numerator here and an x minus 8 in the denominator here. And so all that's remaining now on the top, after I cancel all those things out, is an x minus 3 on the numerator. And on the denominator, I have a 2x and an x minus 9. And there's really nothing more I can do to reduce. Now sometimes I'll see people try to do this. They'll say, oh, well there's an x right here that you can cancel with an x right here. That you cannot do because that x on the numerator is actually part of an expression x minus 3. So unless you have an entire x minus 3, that whole chunk, you can't cancel anything out. So that's as far as we can go with reducing. Now as far as the values that x cannot have, and so we want to give our excluded values, we have to remember that it has to come from the original problem, so before we did any canceling. So we want to look back up here for excluded values, and I can tell that 8 would make the denominator 0. I can see that -3 would make the denominator 0. In the second denominator, I see a 0 would make that denominator 0, and so would 9. So we actually have 4 excluded values. We have 4 values that would make the original problem undefined. So now it's time for you to give this a try. So I'm going to have you pause the video, try number 3. You can tune back in and check your answer when you're done. Go ahead and pause now. So thank you for giving that one a try. Our final expression reduces to 3x over x plus 1 with 2 excluded values, -1 and 9. So now it's time to move on and talk about dividing. Okay, so let's divide rational expressions. So we said that really dividing rational expressions is really only one step away from multiplying. All we simply have to do is change that division sign to multiplication and then flip the divisor. Okay, and so that's kind of just, again, one step away from what we just did with the multiplying. So of course we do want to do any factoring that we can do so that we can cancel out any common values, but so when I do factor this second rational expression there, I'm going to put what was the numerator on the denominator and vice versa. So this numerator was, let's see, if I factor it, it's x plus 7, x plus 2. So now that's going to go on the bottom when I flip my fraction. So that's going to now become the denominator. And what was the denominator now becomes the numerator, and its factored form would be x, let's see, plus 2 and x minus 1, because that is the factored form there then. And now the original rational expression, this x plus 7 squared, so there's an x plus 7, and then there's another x plus 7. So sometimes it means we kind of want to expand this out just so that we see that there's two of those x plus 7s. And now when we go through to cancel, we're sure to only cancel 1 for 1. So there's 1x plus 7 down here. There's 1x plus 7 up here. There's an x plus 2, and there's an x plus 2. And so that looks like, to me, all that can be canceled out. And so what's left on the numerator is the x plus 7 and an x minus 1. And what's left on the denominator is simply that x squared. So that's our quotient between those two. And now we just have to identify the values that would make this undefined. Now this is a little trickier because when you do that here, you have to make sure that you include things from the original denominator as well as the ones that are in your intermediate step here. So we want to look here, but also what the denominator was to begin with, which is now the numerator of that second one. So we have a lot more possible values that could cause us problems. So we know that x cannot be, well, if we look up here in this original denominator, the values that would have made that equal to 0 are -2 and +1. And then now we're going to just look here once we change it to multiplication of the reciprocal and all those values that make that 0. So there's that -2 again. There's a -7. And of course, what would make the x squared 0 is 0. So we have 4 excluded values here, -2, 1, -7, and 0. And our quotient turns out to be, x plus 7 times x minus 1 over x squared. And we'll try one more together before we assign a couple U tries. So again, step 1 is going to be to go ahead and factor, and then we'll switch this to multiplication of the reciprocal. So really the only thing to factor in this first expression is to take the 3 out of the denominator. So if I get rid of that spot, so if I take the 3 out of 3x minus 30, I have 3 times x minus 10. And then I'm going to write this as multiplication. So I have multiplication of the reciprocal. So my second term, when I flip it, what was the denominator has become my numerator, and I'm going to factor that. That'll be an x that I can take out of both of those, times x minus 10. And then that numerator, looks like there's a common factor I could take out of 9, so I'm going to go ahead and do that first. Let me factor this and then I'll rewrite it on the denominator. So that's going to be 9 times x squared minus 3x minus 4. And then when I factor that, so I'll have that 9, but then I can break it down into binomials. Looks like I'm going to be able to do an x minus 4 and an x plus 1. Because now those multiply to -4 and add to -3. And so now I'm going to go ahead and cancel out my common factors. So I can see there's an x minus 10 and an x minus 10. I see that there is I could take a 3 out of itself and out of 6 twice. And I think that looks like all I can do to reduce. So what's left on the top, all these things are left on the top, this 2, this x, and this x. So those multiply to give me 2x squared for my numerator. My denominator, these are the things that are left over that have not been canceled out. There's the 1, which really doesn't do anything. It's 1 times 9, and then each one of these binomials. So that would be 1 times 9, which is 9, and then times x minus 4 times x plus 4. And again, there's really no need to multiply that denominator back out because really it is more useful to us when it is in this factored form because it allows us to see those values that are excluded. So I'm going to go ahead and start with those so I can tell for sure that x cannot be 4. It also cannot be -1. But I need to make sure I look back at this level, and then I have to look back at the original, what was the original denominator as well, because any part of this, you have to make sure if there's something that makes it undefined that we excluded. So the one thing we haven't covered in this denominator, the intermediate denominator here, is that x minus 10 factor. So that tells me that x cannot be 10 here, because that would make that 0. But then when I go back to the original, I know that that factored form, which is now right here on this numerator, is what would make it 0. would be the 10, which I already have listed, and then another value of 0. So this time it has, again, 4 excluded values, 4, -1, 10, and 0, and my final quotient is 2x squared over 9 times x minus 4 times x plus 1. And just as a side note, I know sometimes students will ask if it matters which order those binomials are listed in. No, it doesn't. I mean, you could put the x plus 1 first and then the x minus 4, and that's completely fine. It's all multiplication, so the order doesn't matter. So we're going to go ahead and end the lesson with a couple you-try problems. So I'm going to go ahead and leave these you-tries for you to give a try, and we'll talk about them when we get in class, as well as we'll kind of handle these modeling real-life situations in class as well. So we'll save this whole last page for in class, but I want you to try. So before you end today, the lesson, I want you to do the you-tries before class. So we're going to go ahead and give these two a you-try designator, and we'll check those answers when I see you in class. So thanks for coming.